Hello and welcome. So the other day I thought about teaching my kids how to ride a snowboard, but then I came to realize that they might get addicted to it, and that could be a slippery slope. And speaking of slopes, in this video we're going to learn how the concept of the limit can be applied to rates of change, i.e. slopes of functions. Let's get right to it. Looking at example 1, it says, suppose you drop a calculus book from the top of building 61. This is the math building at Mount Sac. And suppose you figure out that the distance fallen is y equals 16t squared. So y is in feet here, and t is in seconds. The question asks, what is the average speed of the book between 1 second and 2 seconds? Well, to get an average speed, you take the distance traveled divided by the time elapsed. So if we want to think about the distance traveled, we can get the ending distance, or the final distance, minus the initial distance, that distance at the beginning. And that'll give us the total distance traveled. And then to get the total time elapsed, we just take the final time minus the initial time. And then we divide those two. So it'll look something like this. Y of 2 minus y of 1. This is going to be the final position, or distance, minus the initial distance, divided by 2 minus 1. That's the change in time. And in fact, you might have already seen some notation that looks something like this. This is like delta y over delta t, where the delta just represents the change in this kind of variable here. This is the change in the y variable and the change in the t variable. You can treat y as either a variable, like a dependent variable in this case, or you can also treat it like a function. You can think of this as y of t. You can go back and forth between those two thoughts. So y of 2 would be 16 times 2 squared. We're just taking 2 and plugging it right into the y function, thinking of it as a function. And then plug 1 into the y function. Now here I'm just going to leave it as 2 minus 1 because we've got a lot of stuff going on up here too. And when we evaluate this, we'll get 64 minus 16 on the top over 1. So that's going to be, what does this look like? 48 over 1. So that's 48 feet per second. That's the average speed of the book on that time interval from t equals 1 to t equals 2. And you can see that on the top, the number 48 that's on the top is representing the distance that the book has fallen in that time interval. And the 1 is the 1 second that elapsed from t equals 1 to t equals 2. So you can think of the 48 as having the units of feet, the 1 as having units of seconds, so when you divide you get 48 feet per second. Let's look at the next question. What is the average speed of the book between t equals 1 second and t equals 1.1 seconds now? So now our time interval has shrunk. Before it was 1 second, now it's 0.1 seconds. Well, the calculation is the same. In fact, we'll start off with just writing delta y over delta t. Start to get used to that notation in case you haven't seen it. And we'll jump in and we'll say, all right, the final distance is going to be the one with t equals 1.1 plugged in. That's going to be like the final y value, and then minus the initial y value over now 1.1 minus 1. So just to tie it back, this is like our y of 1.1, and this is like our y of 1. And working things out, you have 19.36 minus 16 over 0.1. And on the top, you end up getting 3.36 over 0.1. And dividing by 0.1 is like multiplying by 10, so this becomes 33.6. Again, the units are feet per second. Anytime you have a problem with units, you want to write your units at the end. That sounds like you're having a problem with units. But I mean, an exercise that has units in it, then you want to write the units at the end. We all have problems with units now and again. All right, so we shrunk the time interval. Now we're getting a different average speed. So here's a question. What is the speed of the book at t equals 1 second? So notice that we're no longer given an interval of time, not even a small interval of time. We're just asked, what is the speed of the book at t equals 1 second? I mean, it's got to be something. It's got to be going some speed at that particular point in time. And this would be what's called an instantaneous speed at t equals 1. It's like the difference between when you're driving a car and you're looking at the speedometer and it's telling you exactly how fast you're going at that moment. So let's say you're going 65 miles per hour, exactly the speed limit. So that would be the instantaneous speed. But if you're taking a trip and you want to figure out, okay, well, how far or what is my average speed on this journey? Well, there you would take the total distance that you travel divided by the total time it took you to travel that distance. And that would give you an average speed. Even though your instantaneous speed at any time in the journey could be faster or slower, it gives you an average of what your speed would be on the whole interval. So that's the difference here. So we're looking for the instantaneous speed of this book, given that we know the height function. Well, one approach to figuring this out is to look at what happens when you take the average speed from t equals 1 to t equals another value that's kind of close to 1. And in fact, getting closer and closer to 1 so that your time interval, your little time interval, is shrinking, getting closer and closer to 0, so that it's almost like you have no time interval in the end. Well, we looked at what happened when the length of the time interval was 1 second, and we got an average speed of 48 feet per second. So this is when t went from 1 second to 2 seconds. And we also figured out from 1 second to 1.1 seconds. That was an interval, a length of the time interval of 0.1 seconds, and the average speed was 33.6. That's what we figured out in just a moment ago. 33.6 feet per second. So I'm just copying down our results from the first two. So let's look at what happens when we go 1 second to 1.01 seconds, and then 1 second to 1.001 seconds, and then even farther, 1.0001 seconds. And we'll see if there's a pattern when our time interval shrinks. A pattern or some kind of something that we can get out of this. Okay, so when the time interval is 0.01 seconds, then we get 32.16 feet per second, it turns out, if you calculate all the same stuff that we calculated above. For 0.001 second time interval, we've got 32.016 feet per second, and you can start to see what's going on here. What does it look like the average speeds are approaching as our time interval shrinks down closer and closer to 0? Yeah, if you said 32 feet per second, that would be correct. That's what the average speeds look like they're getting closer and closer to, right? It seems like this decimal just keeps adding more zeros as you go. So it looks like the instantaneous speed then, when we have an infinitesimally small time interval, so an interval of like 0 seconds, then the instantaneous speed would be 32 feet per second. That's how fast the book would be traveling at that particular t value of 1. Now it's important to note that average speeds don't help here. So I'm going to put this note on the side. Note Average speeds, they don't help and they don't work here. Sounds like they're not working here. They don't work at Mount Sac anymore. Yeah, they moved on to another job. So the average speed, if we were to try to calculate it from t equals 1 to t equals 1, right? That's what we'd have to do if we were going to have a 0 width time interval, or a 0-second time interval, and have to go from t equals 1 to t equals 1. If you try to do an average speed calculation of the change in position or distance over change in time, well, there wouldn't be any change in the distance. There wouldn't be any distance travel. That would just be 0. And there wouldn't be a change in time. That would be 0 as well. And so then you're left with, well, what is this? This is indeterminate. This is undefined. So it's hard to know what's going on there. So we can't use the average speed formula that normally works just fine. We can't use it when our time interval is length 0. So this is where this idea of shrinking the time interval down to 0 and looking at what's happening to the average speeds is going to come into play. And what we did here is we essentially just took a limit. We took the limit of the average speeds as the time interval shrank to 0. That's exactly what we did here. So this is where limits can help us determine rates of changes of functions. So moving on to the second page, we can get a visual picture of what we're looking at by graphing that y function, that distance that the book has fallen along the y-axis, and then t along the x-axis. So it's kind of like an upside down picture. If you were to imagine the bottom here being the top of building 61, and then you drop the book off, it follows this kind of a pattern, like a parabola going down. But here, since we're interpreting y as being the distance that the book has fallen, well, at the very beginning it hasn't fallen anything, and then it falls down more and more. So like for example, at t equals 1 second, the book has fallen, it looks like about 16 feet. At t equals 2 seconds, the book has fallen about 64 feet. So there's a visualization of the distance function over time. And to visualize what we did for calculating an average rate of change, so an average speed of the book over a time interval, we can take the two t values of our time interval, like t equals 1 second, t equals 2 seconds, plug them into our function, which you go up to the graph of the distance function, and then the y value of that point gives you the distance traveled. And then plug in 2 seconds, the y value gives you the distance traveled for that t value. And then what you do is you essentially just calculate the, like we did, the change in the distances, which is this vertical distance from one point to the next. We take the 64 feet minus the 16 feet. That was what we did for finding the average speed. And then we divide that by the change in the time. So that's going to be this horizontal change right here. So really what we're doing is we're calculating the slope of this line. So the amount that we go up is delta y, and the amount that we go over is delta t. It's like rise over run. Delta y is the change in distance, which is the rise, and then delta t is the change in time, which is the run. So we're calculating the slope of this line, and this line that goes through 2 points on the graph of a function is called a secant line. So graphically, an average speed is the slope of a secant line. That's what it is graphically. And if we take our time interval and we shrink it a little bit more, like take the t equals 2 seconds and change it to t equals 1.1 second, we're going to get another secant line that has another slope. And so the slopes of these secant lines are visually what the average speeds look like. Now on the right, we've got a line that's going through just one point on the graph here. It's just touching the graph. And this would be called a tangent line because it's just touching the graph right there. It could intersect the point, this tangent line could intersect the graph at other places, but locally at least, it's just touching at one point. And it's going in the same direction as the graph of the function. It's going in that same direction. So it's giving you a sense of how the function is changing at that particular point in time, at t equals 1 second. And this is what we did. We found the slope by just plugging in a bunch of shorter and shorter time intervals and seeing what the average rates of changes were doing, what the average speeds were doing. And they were getting closer and closer to 32 feet per second. And that 32 feet per second is the slope of this line. So that 32 feet per second, that instantaneous speed, is the slope of a tangent line. Below each of these, it gives another quick example. So if you travel 200 miles in 4 hours, 200 divided by 4 it would give you 50 miles per hour. That's an average speed. Whereas instantaneous speed is, I'm going 60 miles per hour right now. Here's a little applet that you can play around with to get a little visual of the slopes of the secant lines getting closer and closer to the slope of the tangent line. So these two dots are representing the points on the graph. And here this dot has a t value of 1 second. This one had a t value of 2 seconds, but now we're shrinking that time interval. And so these dots are going to move closer to each other. And when they do, the secant lines get closer and closer to a tangent line until they're right on top of each other, and then it becomes a tangent line. Now, of course, again, you can't use the average rate of change formula at that point once you're looking at a tangent line. Instead, you have to use this concept of the limits, and we'll get into exactly how we're going to deal with this algebraically in a little bit. So this little note is just saying that the average speeds get closer to the instantaneous speed when the time interval shrinks. Now, generalizing from average speeds to average rates of changes in general for any kind of function, a lot of times we're using f of x for representing a general function, like abstracting it. So in general, we can say that the average rate of change of a function y equals f of x with respect to x over an interval from a to b. So here x is starting at a and x is ending at b, is like this. It's delta y over delta x, just like our delta y over delta t, but now we're using x instead of t. And if f is representing the function, we can write this as f of b minus f of a. That's the change in the y values, or in other words, the rise, over b minus a, which is the change in the x values. So this is a little picture of that. And here you have your starting x value, your ending x value, and here's your starting y value, your ending y value. So once again, you're just calculating a rise over run. Rise over run. The rise will be f of b minus f of a. So I'll try to squeeze this in here. And then the run is going to be b minus a. It's the right x value minus the left x value. Now, another way you can represent this, and one that we're going to be using coming up soon, is instead of having these two separate x values of b, a, and b, we can relate them by calling the first one a and the second one a plus h. That way, this distance between the x values is represented by a single letter, a single variable, which is h. H is just how far you're moving from A over to the right. So it's that horizontal distance. And that's the thing that's shrinking down to 0. So it's convenient to have a single variable representing that, because to make this interval shrink to 0, you can let h approach 0. So you can take the limit as h approaches 0, as we'll see in a second. So this is just another way of representing the same idea. Here the slope of the secant line is going to be vocal malfunction, f of a plus h minus f of a, and then the run is just going to be h. You can write a plus h minus a, but then the a is canceling, you just get h. So that's where this expression comes from, f of a plus h minus f of a all over h. These are sometimes called the difference quotient, because you have a difference, either both on the top and the bottom, and then the quotient being the division, the fraction bar. Let's now bring in the limit. Bring in the limit! As the h value, which is our interval width, approaches 0, the slopes of these secant lines are approaching the slope of the tangent line. So with limits, we can write the tangent slope like this. It's the limit as h approaches 0, as that interval shrinks down to 0, of the slopes of the secant lines. So that's going to be the f of a plus h minus f of a all over h. Let's look at this visually one more time. So if h is shrinking down to 0, then this right x value is going to be getting closer to this left x value. So the slopes of the secant lines are going to get closer and closer to the slope of the tangent line at x equals a, until it's right on top. And I mean, in the limit, it's actually never exactly on top, but in the limit, it gives you the slope of this tangent line. Looks like it has a negative slope because it's going down as you go to the right. And all of these, all these text fields collided with each other. A and a plus h, they all collided. So coming back to the notes, the name that we give this particular limit is called the derivative. Of f at the point A. And it's written f prime, so this little apostrophe looking thing is called prime, and so it's read f prime of A, f prime of A. So now we've got three interpretations of this limit as h approaches 0 of the difference quotient, or of the slopes of the tangent lines. So we have three interpretations of this. One is that this is computing the instantaneous rate of change of f with respect to x at x equals a. This is like on the first page of the notes, where we looked at the shrinking time interval and looked at the average speeds, thinking about what are those average speeds approaching. So they're approaching the instantaneous speed, or in general, the instantaneous rate of change of a function. Then we looked at it visually, and we saw that this concept visually looks like a bunch of slopes of secant lines getting closer and closer to the slope of a tangent line. So in the limit, we get the slope of the tangent line at x equals a. And now we're introducing this new vocabulary, the derivative, and representing it with f prime of a, where the prime again looks like a straight apostrophe. Let's mosey on down to example 2. Here we're asked to find the slope of the tangent line to the curve f of x equals 5 minus x squared at the point P of 1, 4. And on the right, there's a picture of 5 minus x squared drawn, and the point P is there. It's 1, 4. So if you had to put a little y scale, that would be 4 right there. So P is 1, 4. Now the approach we're going to take is just like we have been doing. We're going to move a little to the right of the x value at which we want the tangent line and get some point. We'll call it Q. Now mind your P's and Q's. So we'll call this Q. So this Q is just a little bit to the right of P. And so we're going to say that the x value of q is 1 plus a little bit, plus h. That was the variable that we used to create that little interval in x. So if that's the case, if q is at 1 plus h, then what would the y value be of q? How can you get the y value, knowing that the point is on this graph? Yeah, you just take the x value, which is 1 plus h, and you plug it into the function. So it's like f of 1 plus h is what you want to find. So this would be just f of 1 plus h. Now we'll go through and figure out what that looks like. We'll plug 1 plus h in place of x here, so we'll have 5 minus 1 plus h squared. But we'll do that in just a moment. Let's start getting into the algebra. Well, first off, let's write up what we said the definition of this slope of the tangent line is going to be, or how we're going to write this out. So the slope of the tangent line at x equals 1 is going to be, the limit as h approaches 0 of f of 1 plus h minus f of f of 1, all over h. We just filled in a, we replaced the a here with 1. A was representing where we wanted, it's like the x value where we wanted the slope of the tangent line. So in this case, we want it at x equals 1. So we replace the a's with 1. So next, we can take the 1 plus h, plug it into our function, and we'll get 5 minus 1 plus h squared minus, and then take the 1, plug it into the function, and we'll have 5 minus 1 squared. Now here's a super common mistake, which is to leave it like this. But what's wrong here? If you picked up on it, we want to be subtracting the entire f of 1. We want to subtract the result of f of 1. We don't want to just subtract part of the function. We want to subtract the whole result of the function when you plug 1 in. And so if you plug 1 in, we should get 5 minus 1, which is it was my 5 minus 1 squared, which is going to be 4. So we want to be subtracting 4. But if you look at it, as it stands, we're not subtracting 4. We're doing minus 5 minus 1. That would be minus 6, not minus 4. So what we've got to do is, if we're going to subtract this whole function, we're going to have to put parentheses around it so that we finish computing what the output of that function is first, because it's in the parentheses, and then subtract that result. So the main thing is, when you have this subtraction, if f has more than one term, like it does here, like 5 minus x squared, so if it has lots of pluses and minuses, you have to make sure all of that's around parentheses so that you finish computing what's inside, or at least distribute the negative to all the terms, and then everything will come out okay. All right, so then we have all over h. So now we can take the 1 plus h and square it, and then note that this negative will distribute to all of those terms after we square. So we're going to have minus 1 minus the 2h that you get in the middle, minus h squared. Don't forget that middle 2h. When you expand something in the form a plus b squared, you have a 2ab in the middle. It's not just going to be the first thing squared plus the second thing squared. Okay, so this evaluates to the 4 that we talked about earlier. Let's keep going. Notice that here we're going to get 5 minus 1, which is 4, minus this 4 gives you 0. So the 5 minus 1 will cancel with the 4, in other words. So you'll get negative 2h minus h squared over h. Now we can simplify even further. Now we can take each of these terms on top and divide by h. Or you can think about factoring an h out of the top and then cancel that factor of h from the top and the bottom. I'm going to go with dividing just because then I don't have to write the extra step of factoring. So dividing each of these terms by h, I got negative 2 minus h. So now what's the limit as h approaches 0 of negative 2 minus h? Negative 2. There, all we did is, to find the limit of a polynomial, we plug in the variable, what the variable is approaching. So replace h with 0, and we've got negative 2 minus 0, which is negative 2. So the slope of the tangent line at this point, or at an x value of 1, or you can say the point, which is 1, 4, the slope of that tangent line is going to be negative 2. And that's the tangent line, not the secant line. So if we draw a tangent line, just barely hitting it right there, that has slope negative 2. That seems about right. It's negative. It's definitely going down as you go to the right. Okay. One other thing that I wanted to mention is to note that all these derivatives, they're all indeterminate type limits. They're all 0 over 0 type limits. And this is one of the reasons why we spent a bunch of time talking about 0 over 0 limits, that we could tackle and have the tools for evaluating derivatives by the definition, by the limit definition that we just covered. It's going to always be 0 over 0 because, let's take the most general form, because if you plug in h equals 0, then you get f of a minus f of a, which is 0 on top. And then if you plug in h equals 0 on the bottom, you get 0 on the bottom. So these always turn out to be 0 over 0 type limits. But thankfully, we can handle 0 over 0 type limits. We look for factors that are causing the top and the bottom to be 0. In this case, it was the factor of h that was causing the top and the bottom to be 0. Once we canceled off that factor of h, we were able to plug in the h value that we were approaching. Now the next question is, find an equation of the tangent line at P. Well, we have the point, that the tangent line goes through. It's 1, 4. That was just P. We have the slope of the tangent line. That we figured out a moment ago. That's negative 2. So we're going to use point slope form to get the equation for this tangent line. Remember that point slope form is y minus y1 equals m times x minus x1. Here x1 comma y1 is any point on the line, and then m represents the slope of the line. So we're going to use the 1, 4 as our x1, y1. And just feed this into the point slope form. Now I'm going to go ahead and box this. This is an equation for the tangent line. Sometimes you'll see it, though, solved for y. And the way you can do that is distribute the negative 2 and add the 4. This would be called slope-intercept form, which you might recognize from your previous algebra and pre-calculus courses. Remember, it looks like y equals mx plus b, something like that. I'll write that a little bit better. Okay, but either one is fine for our purposes here. Sometimes it's nice to write it as a function, but other times we don't really care and we just leave it as in point slope form. All right, so that's the equation. So when we see that equation, this is the equation. We have to have that equal sign. That's the part of the equation. So then it says find f prime of 1. So what does this mean? This means the derivative of f at 1. But we were just saying a moment ago that the concepts of the slope of the tangent line at x equals a and the derivative f prime of a, they're exactly the same thing. If the slope of the tangent line is negative 2, then the derivative is negative 2 as well. And the instantaneous rate of change is also negative 2. So here we'll just write negative 2. Find the rate at which f of x is changing with respect to x at x equals 1. it's -2. All of these concepts are the same. That's a good place to end this part. Thanks for watching, and see you in the next part.